Hello and welcome to this series of lectures on basics of control with potential applications to EV. So, before we start control design, we will see first what control can do, what could be our objectives, and I'll start again with this little example where we had a car which we wanted it to go at a certain speed with a certain, based on that we calculated a certain reference for the open loop and closed loop. We also saw that the response was faster in case of the closed loop than in the open loop, which is a kind of not surprising. So, what else could happen while we while the car is running? So, we can have disturbances in terms of the percentage slope of the road, either be an uphill or be a downhill. And we'll see, we actually saw what happens in what cases does the vehicle come to a complete halt, and in what cases the speed starts from say certain 10 kilometers an hour and then going to 100 kilometers from hour. When I am driving a car, I want neither of these situations. I do not want my car to stall only because I am on an upslope, and I also do not want it to overspeed only because it is on a downslope. And with the controller, which was just a gain, so to speak, this was not possible. We could see that the vehicle stalled and the vehicle was going at arbitrarily large speed, right. So, we calculated some questions. So, what was the steady state speed for open loop, closed loop, and find the steady state error. So, a little departure. So, what I do is in this I will set my speed to 60, the reference speed to 60. Earlier we had calculated that if this was 60.8, this became 60 and so on. So, to get a desired speed of 60, I had to set the reference to 60.8, which means there was always a certain steady state error between the reference and the actual. And of course, I could increase the gain k to reduce the error, but you cannot make it to 0. Okay, so this is the steady state error that I seek for the given values of k. If I this will be maybe some 59 point something. So, there is a steady state error in the tracking reference speed. So, what I now do is, if you look at the construction here, the throttle control is just, so this k1 was equal to 50. What I do now is I do k1 is 50. I add to this a term which is some constant divided by s. Largely this is 1 over s corresponding to an integral kind of action. Okay, so with this something interesting happens, right. So, for ki equal to 0, this is the blue line, this is the one which gives a certain steady state error. Okay, now I put ki to 5, which is this red line heading here, all the way till ki equal to 30. So, what we see, the commonality is that if the reference, this is my reference speed is 60 and my actual is also 60, right. So now in my earlier version, for this to, maybe I will just use another color. Okay, so for this to be 60, this had to be 60.8, or in other words, also if this was 60, this could be some 59.3 or something like that. Now, and that was when the control was just a number 50 here, right. The throttle action is just 50 degrees per kilometers per hour. Now, if I add an extra term KIS, I start with this 50 here, this 60 here, and what I see is that in the steady state this also goes to 60. So, the steady state error is eliminated when I just add this, when I just add a extra term of this form Ki by S. So, so just do this. So, I have K1 plus Ki by S, and for different values of Ki you see a slightly different transient response, but the steady state remains constant at 60. Okay, this is nice. So I had a certain error and I could eliminate that. Other thing that we saw is calculate the upslope that will cause the vehicle to stall if it was running at 60 kilometers per hour. Okay, and assume that the reference is assumed constant. So I'll again assume that the reference is now at 60, not at 60.8. Okay, so what happens? So I start over here, and I see the following happens, right? So when the controller is just K1, right, and then there is no Ki is 0. So what we see, just look at the blue line. So I start here, I go closer to 60, and after some time my speed just goes to 0. Okay, so there will be a little steady state error here, but here my speed goes to 0, right? So this is the stalling of the vehicle. So what I do now is I put a small ki at 5, and you see, okay, the speed is actually coming closer to 0. It's kind of slows down, but eventually picks up, right? So there is maybe if you can kind of see this in a car which has a cruise mode, right? You set the car to a cruise speed of 60, and say you experience a uphill. What you'll see for a while is instantaneously you'll see a dip in speed. Maybe it goes from 60 to say 55, but eventually it picks up. You'll actually see the control adjusting itself to retain the speed at 60, and also you'll see if you go downhill, the speed increases and your car will have some kind of a braking action and so on. So what you see here is for different values of ki, your speed, so for ki equal to 5, my speed falls till 5 and then increases until ki equal to 40, where the speed falls to say about 20 and then increases again. Of course, if I keep on doing this and I have a much larger value of ki, the speed may not fall as much as maybe for certain values I can just design it to be that it will just go, speed will go down slightly a little bit and then again catch up very fast. So this is the effect of adding K1 plus Kd over S, K1 plus Ki over S, right. So the vehicle which earlier stalled due to a constant throttle angle of 50 degrees has now recovered and it has regained its original speed. Okay, now I could also do responses with different values of Kd. So my controller will now have a K1 Ki by S. I also add something S Kd times S, and you'll see here different kind of responses, right. So so things here are recovering maybe a little faster, right. So for different values of Kd, you see that the response actually becomes a little faster and things settle down at maybe a little faster pace. Things start recovering also a little quicker and so on. So this comes with the action of S times Kd of S. Okay, so what is the maximum permissible downslope for the vehicle not to exceed 100 kilometers per hour if it was running on a steady road at some speed of 10 kilometers per hour. So now what we had earlier calculated, but for the output to be 10, my reference had to be 10.133. Now with the controller of the form K1 plus Ki over S, I could just have this as 10 and this would also be 10 at steady state. Okay. Now how do I visualize this, right? So a vehicle running at a constant speed. So I was at 10, I encounter a disturbance with my controller with K1 equal to 50, I accelerate immediately to 100 kilometers per hour. Okay, and this is not a desired behavior, right? The disturbance actually has a very bad effect that my speed increases almost like 10 times. Okay, what do I do now with an integral action? So this is with only K1. Okay, now I increase the values of Ki So Ki equal to 10, I actually hit a very high speed before I come back, right? And as I keep on increasing the values of Ki, my top speed reduces. It starts from about 91, 92 to go till 80. And for you can try and simulate this for say Ki equal to 300, and then check that maybe it doesn't, the speed doesn't go beyond or doesn't go up like as high as 10%. So within some reasonable limits, you can stop the speeding. You don't need to go till 90, 80 or 70, right? Okay, so with so how do we choose now a better response, right? What is my design specifications, right? So based on certain specifications, could be that I should not reach this 80, maybe I just want to go till only maybe this much is allowable. I am not allowed to speed beyond 30 kilometers per hour, or even sometimes just beyond 20 kilometers per hour. You can actually check and simulate this, right? For different values of Ki, how can you maybe limit the top speed to say 30 or 20 and so on. Okay. Now, if I add a derivative component for larger values of Kd also, I see I can maybe reduce the effect, the top speed much faster than I could with a controller of the integral form. For Ki equal to 30, I'm still around 80, right? This doesn't change much, but with a derivative control, I could change this till it starts at 80 and then it goes 70 for some fairly smaller values of Kd like 20 as opposed to Ki of 30. So I can still keep on increasing my Kd and then see, okay, maybe having Kd maybe reduces this faster than having a very large integral control. So this motivates for me two things of first is that when I had an error, right, for when the input was 60.8, output was 60, right. So if I wanted 60 here, I had to set this to 60.8, right, the reference and the output. Now I just add a integral component Ki over S, so that gives me that there is no longer a steady state error. Not only that, my vehicle which was earlier stalled now continues to move and then eventually recovers to its steady state speed or the desired steady state speed, which is 60 kilometers an hour. Also with the addition of derivative control, I could do things a little, the recovery and all could be a little faster, right, as we see from these pictures. Okay, and then same thing I could do even on a downslope where my vehicle went from 10 to 100 in like less than 2 seconds. I could with the help of integral action get the speed back to normal, and with the help of derivative action now could get the vehicle back to normal faster and also without hitting too much of high speed, right. So these three actions which we did, we just increase or decrease K1, then we added an integrator Ki by S, and then we added a derivative component S times Kd, which now motivates our study for PID control, which we will do in the next section of this lecture. So just building up on the examples that we considered and how we could mitigate disturbances of the car when it's going either upslope or downslope, how to fasten the response and so on, we are now ready to formally introduce the notion of what is popularly known as PID control. The term P stands for proportional, the term I starts for integral, and the term D starts for derivative. And of course, as the name goes, so proportional will just have a Kp term, the Ki will be an integrator and a derivative term. In the Laplacian domain, they will correspond to a constant 1 over S and a multiplication by S respectively, and together we have some gains which we are free to choose, and we also seen how for different values we get different kinds of responses. Okay, so first we will do something, right. So my typical performance criteria can be classified into two. One is the transient response, where I am looking at how fast my system responds, what are the overshoots, what is the settling time, and based on the system at hand and my design constraints, I can design systems either to be underdamped or overdamped and so on. And at the steady state, I want the steady state error to be eliminated completely. If not, at least I want to reduce it to a very small number. And also the idea is to reject disturbances. Okay, so the first thing we will look at is what is the effect of adding a 0 on the response of a second order system, right. So we just add a 0 at minus alpha zeta omega n, nothing changes, is just to maintain a DC gain of 1. So my output will have the original output plus the derivative of the original output, if I just look at it in the Laplacian domain. And if I do the inverse Laplace, I have the total output is the output and some term related to the derivative of the original output. If alpha is large, then the effect will be very less, right. You see what is, because the alpha is sitting in the denominator, right. And then if alpha is 1 or something closer to the origin, then we see that the effect of the derivative term has significant impact on the overall output. And now we will also see why this derivative term and what is the relation with the D term in the PI and D. Okay, so I have here step responses for different values of alpha. So for alpha very large, so this is the green line, which is almost as if the 0 does not exist. Okay, so let us look at alpha is 0.5. When alpha is 0.5, so this I can look at this as my original response of the system. I see a significant increase in my overshoot. For other alphas, alpha equal to 1, my overshoot is here and so on. Similarly, for alpha equal to 6, I have a value here, alpha equal to 10 and so on. So as alpha grows or goes closer and closer to 0, we see a significant rise in the overshoot, even though the response is faster. So whenever we have overshoot and the overshoots increase, a good thing of that is that the response of the system is faster. And this is the same plots for different values of zeta. Okay, so what we see is that there is a increased overshoot. There is no effect on the settling time. So largely, if you see here, the times are the same when the plots go towards 1. The response is faster, of course, for smaller values of alpha, and as alpha goes to infinity, the contribution of the 0 decreases, and when we recover the original system. Okay, so similarly, what is the effect of adding a pole? I just add a pole at the location again at minus alpha omega n, and what I see is I'll just skip the mathematical details. What we see again is that as alpha goes to infinity, the contribution of the poles reduces, and we reduce when we get back the original behavior. So that's not very exciting for us. As alpha, okay, let's see for what happens for alpha equal to 10. For alpha equal to 10, I just see that the response slightly shifted to the right. Okay, and then as alpha becomes say if I take a value of alpha equal to 1, the overshoot disappears and so on. So we can expect different kind of behavior for different values of poles. To summarize, we have the original plot, and then as alpha gets closer and closer to the origin, the response shifts. For example, for alpha equal to 0.5, we'd actually see an underdamped response. Okay, so that brings us to a situation where we now want to actually formalize it. How do I choose this? So I know if I add a 0, I have some kind of a derivative action happening. If I have a pole, I have some kind of an integrating action happening, especially when I have the poles closer to the origin. Okay, so in the proportional control, what happens is I just have a number Kp sitting here. right? And then the input u is, so this is E of S, the input u is just a function or linear function of k of the error, and the transfer function or the controller transfer function is simply Kp. So, if I look at a first order system, what happens is, so if I have a system of the form Ts plus 1, the steady state error has the form of 1 over k plus 1. Okay. So, what I have seen is that, what we see is that the proportional control has improved the time constant from t to t over 1 plus k. Okay, but then there is still a non-zero steady state error. So, what we can do here is, this steady state error can be reduced by choosing a large value of k. Of course, a large value of k might have, sometimes system can go unstable, and also it is not really good when we have noise terms in the system. Of course, things are not just about stabilizing, right, or things are not just about having a finite steady state error. So, we also have to look at what happens to disturbances, and what if the plant is of higher order, no, well, and anything like this, will it work or not. So, if I so let's do a little bit of analysis on this, right. So, if I have just a Kp, a second order system of this form, what happens with Kp is, so this is my original characteristic equation. With Kp, now I have a characteristic equation which is like this, and what we see is that in this characteristic equation, this term is related to zeta and omega n. This term is only related to omega n, or the natural frequency of the system. So, when I add a proportional control, the S coefficient remains as it is. Only thing I have flexibility is in this term, right, and only thing that can be controlled is the constant term A plus Kpa by selecting an appropriate Kp. Now, this determines the natural frequency, but at the same time I cannot control the damping of the system. Okay, so here we see a response of a second order system to different values of Kp, with the reference value being 1. So, if Kp is made large for a small steady state error, here you see, right. So, I have Kp, the steady state error increases, and this is for Kp equal to 20. For a very small Kp, I have a very large error, and so on. So, if Kp is made large to get adequately small steady state error, the damping may be much too low for the satisfactory transient response, because you see a significant overshoot over here. So, if I look at a thermal control system, right. So, where I have a transfer function of this form, the goal is to design a controller to track a reference input temperature signal RT, which is a ramp of close to 30 seconds of 30 degree per second for a duration of 30 seconds, and a steady state value of 300 degrees Celsius. So, it will be something like this, right. So, my reference signal now is from here, this is at a slope of 30, and then after a while I just want it to become 300. So, this is my reference signal. So, can I use a proportional control that minimizes the tracking error and and therefore the steady state error. So, this is how my mathematically it would look something like this, with this being my closed loop transfer function. Okay. So, I look at what the steady state error is, and so on, this little computations of how I compute the steady state error, and what we see is that proportional gain of 0.03 corresponds to a damping ratio of 0.3 and resulting in a DC offset of 10 degrees. So, okay, so maybe this is a better picture to depict this. So, I have the reference input is the red line. When I have a Kp of very small value, the blue one, I see that the system comes and stabilizes at some value which is say about 260 or 270. So, you see a bit of error over there, a steady state error. I keep on increasing to 0.03, the error decreases, and until I reach the value of Kp where the error is like quite small. Okay. So, now what does the first statement mean? The first statement means that uh, if I just have if I'm just having a reference as a ramp at steady state, the proportional control will only go away, and that you can see in this pictures also, right? That this distance for the green and the blue curves is kind of increasing, right? So, as time progresses, the distance will just diverge and the steady state error will be infinity. However, at this point my reference changes, and that kind of makes things a little easy for me. So, it will actually be a step reference from then on. A step reference for a uh, type 0 system will have a constant steady state error, right, and that's constant steady state error is given by this number over here, right. So, for Kp equal to 0.03, we can compute the steady state error to be 10 degrees Celsius, right, and for times less than 0, because of obvious reasons of the type of the system, the steady state error will go to 0, right. Okay. So, so this is how a proportional control works. Okay. Now, summary. So, what we see here is that okay, so this can be easily checked, right. So, the effect of disturbances will not be captured, or in the sense that the error due to disturbance will also decrease as the gain Kp is increased, but the damping will degrade. Okay. Similarly, on the right hand side, we can see how the error behaves for different value, and see that the error keeps on increasing. This is again for the t between 0 and 30, where my reference is a ramp, and as this keeps going, the error will just become infinity, right. And this is for Kp is 0.1, for Kp is 0.3, again the error is keeping on increasing, but it will, so you will have a steady state error here, where the difference is about 10 degrees, and as Kp goes to 1, the error becomes significantly small. So, if I look at here, for Kp equal to 1, the steady state error will be 300 by 1001, which is almost like 3 by 10 is about 0.3 and so on, which is fairly small enough for us to ignore. Okay. So, what is the summary of this? So, if I just take the same system, I look at the step disturbance, the error will also decrease as the gain is increased, but then of course the damping will degrade, as we saw earlier. For systems of large order, increasing Kp might lead to an unstable system, right. So, any type 0 system, right, this is where there is no poles at the origin, with proportional control will always have a non-zero steady state error in reference when it is tracking a constant reference input, and it will not be able also to completely reject the effect of disturbances. Okay. Now, therefore, we will see, okay, what else can I do? I can just keep on increasing or decreasing gain, or I can do something better, and that is where we will look at the the integral control. Okay. So, what happens in this case is that the feedback is linearly proportional now to the integral of the system. So, instead of just a Kp, now I have an integral term Ki over S, which means that the input is now the error integrated multiplied by some tuning constant. So, the control signal at each instant of time is a summation of all past values of the tracking error. So, I remember, I accumulate all the errors, and then I see if there can be a corrective action. So, the transfer function is simply given by Ki by S. The controller transfer function is just Ki by S. Okay. So, what happens in this situation? So, if I look at, so this is what the integral action does. It remembers the past values, okay, and eventually the error goes to 0. Okay, so to begin with, we'll start with an error of 1. The error will keep decreasing as it goes to 0. If I experience an overshoot, it will go in the opposite direction and then slowly damp out to 0. Okay, so for a closed loop system, the tracking error with respect to reference is something like this. The tracking error with respect to disturbance is taken care of this one, and this takes care of the noise term. So assume there is no disturbance. We first look at assume there is no noise and there is no disturbance. My interest is how close y can get to r, or how close e can go to 0. Okay. Now, if my reference is a unit step, the integral with the integral control action and the unit step input, the steady state error will always be 0. We have seen this with respect to a type 1 system. Type 1 system, it has an integral component or a pole at the origin. Okay. So, now similarly, if I were to look at what happens to the output at infinity, the output at infinity becomes 1. What happens to the control at infinity? Well, the control at infinity is simply g of 0 with the inverse, right. So, the steady state control is a certain constant number and is equal to the DC gain of the plant. This also means that once the plant reaches steady state, there must be some control input that should be holding it there. Just like if I were to lift a drone and I just want to put it at this location, there must still be some control input. The motors must still keep on giving some energy to the propeller so that a certain distance is maintained, right. So, the steady state control is equal to the inverse of the DC gain of the plant. Okay, I am also interested in what happens in the disturbance rejection. Now, assume that my disturbance is a unit step of the form 1 over s with the transfer function. Okay, this also I can check that this is again it's a small expression to check y at infinity goes to 0. Okay, and u at infinity is -1, and y of infinity is now only because of the disturbance. I do not consider the reference. I can at the end, because of superposition, add both of them, right. So, thus the steady state error is 0 in the output, and the final value of the control cancels the disturbance exactly. Okay. Now, which means that the integral feedback results in 0 steady state output error, both in tracking, as we saw here, it perfectly tracks, and it also perfectly rejects disturbances, right. So, that is one step further, right. We can reject step disturbances, we can also perfectly track a step input. Okay, I will just use the same example where earlier we had a certain steady state error depending on the value of Kp. Okay, so I just do the math. This is easy to follow. What I see is that for different values of Ki, I always reach the steady state, or in other words, the tracking error always goes to 0 for different values of Ki, and what different values of Ki do is just to see how a little bit of effect on the transient response of the system, right, where for a value of Ki equal to 0.03, I see maybe a slightly lesser overshoot and so on, and then this is my reference here. And what we also see is that the error now with respect to ramp is also kind of decreasing, right. So, in the earlier case, for the first ramp, the error was always increasing, right. So, in this case, so if I just look at, just compare quickly. So, these plots were originally diverging, right. So, the distance between the shaded or the dotted red and the blue is always increasing and the green is always increasing. Here it decreases and decreases, and if I just go to the steady state, it just stabilizes to a certain value. Okay, now that is good. I can reject disturbances as well. Okay, now the last component that is of interest is the derivative control. So with the integral control, we could eliminate the steady state error for a step input. We could also eliminate constant disturbances, right? So now the derivative goal of the derivative control. Now we see, okay, what is remaining now? I did take care of the steady state performance via the integral control action. What happens to my transients? How do I control my transients? So the goal of the derivative control is to improve closed loop stability as well as speeding up the transient response. So in the derivative control, the input or the control law is just a derivative of the error signal, and then there is a gain which is called as the derivative gain, and therefore it comes with a transfer function of a kd times s. Okay, so the derivative control is never used by itself, it is usually augmented by a proportional control. So you have Kp plus Kis. Okay. So the key reason is that the derivative control does not support give information on the desired end state, right. So if Gc is 5 at the steady state, it will just maybe go to 0. That is also called the blocking effect of a 0. If the error were to remain constant, the output of a derivative controller would be 0, and a proportional or integral control would be needed to provide a control signal at this time. Okay, that is another feature of this one. So key feature of derivative control is that the derivative control knows the slope of the error. For example, if the error is increasing at this rate or at this rate, the slope will tell me how fast or how slow the error is increasing, and therefore it is, and based on the derivative component, if E dot is say 25 as opposed to E dot is 5, we know that the number 25 says that the error is fast increasing. So I have to kill the error faster, or if the error is slowly increasing a little slower, also take appropriate corrective action. One disadvantage of course is that it tends to amplify the noise, but this also can be corrected by designing and putting in appropriate filters. So as a summary of what we have seen is that I look at the proportional controller, the rise time decreases, overshoot increases as we saw, steady state error reduces, but it does not go to 0. Stability, well, it may oscillate, response to sudden changes is immediate, noise sensitivity is low, and it just used for very basic control. Similarly, I look at several features of the integral control. It just looks integral control helps in eliminating my steady state error, and derivative control improves stability of the system. So each of these we will see in a little bit of detail in forward. So to start with, I will use a proportional plus integral control, and also the reason why we purely do not use integrator or purely you do not use derivative control will be a little obvious from now on. Okay, so I have the proportional plus integral. So I have E of t term and integral of E of t, resulting in a transfer function for the PI control of the form Kp plus Ki over S. So this combination will allow for a little faster response, because we know that a little bit of Kp had some influence on the transient response as well. Okay. Now in addition of this raises the type of the system to 1, and therefore it can reject constant disturbances and also track a step reference carefully. Okay, so if I look at a second order plant, right, this is a rotational element of moment of inertia J and a viscous friction B. Okay, so the error component now with respect to disturbance takes this form, resulting in a steady state error of minus T over K, right. So this is just with a proportional controller. So steady state error with a proportional control is minus T over K. The idea would be to increase k to reduce ESS. Now, if I put an integral control, what happens is, okay, I have this one, my system type raises to 1, resulting in a steady state error of 0, right. So, the proportional plus integral control helped eliminate the steady state error. But what we have to be careful is to check for stability, right. So, all the time, so if I look at, so this will not be stable for all values of, okay, j and b are given, but I have to choose k and k over tau I or Ti carefully, such that I maintain stability, right. So, T and Ki must be chosen such that the roots of this system have negative real part. So, that is a little extra care that we have to take. This will make sense only if the system is stable. Okay. Now, I just go back to the same example. I have a controller of the form 0.03 plus 0.03 by S, and I see something nice happening. So, from the reference till the output, everything is fine except a very small overshoot, which is tolerable. Okay. Now, PI controller. So, what have we observed, that compared to a proportional controller, the PI control system has a 0 steady state error. The P plus I term helps achieve faster response by applying an immediate correction action to the proportional error, right. So, this contrasts with the I controller, which only accumulates the past error, making the system slower to respond changes. So, P plus I is a better bargain than just completely I, even though both PI and I completely eliminate the steady state error. Okay. So, if we compare the time taken, so I think we just look at these two, right. So, with a pure integral control, the same example, it took about 150 somewhere here to stabilize, fairly large time. And if I look at a P plus I control, it stabilizes much faster, say somewhere around this. Okay. So, the system took 170 seconds to reach a stable state with the integrated control alone, but things have improved to 34 seconds now with the help of a PI controller. So, in isolation, both may give individual effects, but together they will do a lot more than just individual controllers. So, similarly, I look at what is the effect of a proportional plus derivative control, which has now a transfer function of Kp plus skd. Kb and Kd, of course, are the gains that we can choose, and the derivative acts on the rate of the change of the error signal, and the output is also proportional to the rate of the error signal. And as I said earlier, I can anticipate the error, and when the rate of error is high, I can take a corrective action immediately. Right. Okay. So, now we will see how this effect can be improved, can be noticed with the damping in the system. Okay. Now, suppose I have a system of the form J(S square), this is my plant, right. A proportional control will lead to a transfer function only of J(S square) plus k. And if I look at J(S square) plus k equal to 0, the roots will only be imaginary, and therefore, the response is also only oscillatory. Okay. Now, if I choose a proportional plus derivative control, I get output of the controller of this form. Okay. So, what is the effect of this? Now, the output, so or the transfer function, which was originally k over J(S square) plus k. So, if you see, there is no damping term here. It says J(S square) plus 0 times S plus k equal to 0. The coefficient of S is where the damping sits in. If damping is 0, system will always be oscillatory. Now, I add the derivative term, it adds a term here, k times TdS. And for positive values of k, t and j, the system is always stable. This for second order system is kind of easy to check, right? For as long as the coefficients are greater than 0, the system will always stable, right? And whatever sits in here is only due to the derivative action, right? So this also means that the P plus D control can be used to change the system damping or shape the system damping, thus having an effect on the peak overshoot. The peak overshoot was something of e power minus pi zeta by square root 1 minus zeta square. It depended on the zeta. Okay. So therefore, the PD control, since it directly has an effect on zeta, can be used to improve my transient behavior. Okay. So if I look at the entirety now, so I can have a proportional control which directly is a function of the error. Integral control, it integrates the error and the derivative component which has the E dot component together with the transfer function of the controller will look like this. Okay. The controller also allows to stabilize an unstable second order system, right? And then, well, through appropriate design specifications, I can choose my Kp, Kd and Ki appropriately, which will lead me to a desired transient, desired steady state, and also keeping in mind stability of the system, right? And because there is a S sitting in the denominator, I have perfect tracking and I also reject constant disturbance inputs, right? So this is how the full controller structure looks like. Okay, so we made a statement here saying that the controller allows an unstable system to be stable. Okay, so let us start with an unstable system now. So I have S square minus B, so the system is unstable because there is one pole which is on the right half plane, this is square root of B and this is the negative of square root of B. Okay, so if I just do a proportional control, what happens is I have S square minus B plus KB. So what I can just do is I have poles here. At best I can move as Kp increases, and when Kp becomes greater than B, my poles shift now to the imaginary axis, which means at best I can do a marginal stability. Okay. So now if I do a derivative component, okay, things are a little better. So what I do is that, so here I have a marginal stability. Marginal stability means a oscillatory response, right? So I have transfer function of the form Kp over S square plus some number here, some constant K. Okay. I want to add now damping to the system to dampen the oscillations, and what I know is that I can do it very well with the help of a derivative component. Okay. Now for Kd greater than 0, Kp greater than B, system is stable, and then I can choose my Kp and Kd such that I achieve the desired transient response, right. So first thing I have done is, with the help of my P controller, I can make an unstable plant to be marginally stable, and with the help of the D component, I can make the marginally stable to be asymptotically stable. Okay, good. So now this system will have a steady state error because there is no, see this is a type 0 system, no integrator. Okay, so just what do I do with the steady state error? I already know the answer. I just add a integral term here so that the system becomes stable. Now because of the integral term, I also know that I have perfect tracking. In addition, I also know that integral control rejects constant disturbance inputs. Okay. So to summarize, we have seen different components of a controller, starting with proportional controller, its advantages and disadvantages, integral control, how it helps eliminate steady state error and also can reject constant disturbances, and derivative control of how it helps improve my transient response. So this concludes the part of basic control where we look at P, I and D components. In the next lectures, we will see a different representation of systems in terms of the state space realization of systems. That's coming up in the next week's lectures. Stay tuned and thanks for watching.